Hello and welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. Tonight we are going to be just having more math discussion while we're waiting around for anybody who comes in and has any particular questions that they want answered. Um, let's see. Last week we were talking a bit about a theorem that one of my students had been working on. She has been out of my care for several years, so I said, well, why not just share some of that work out with the rest of the class here. Don't think. I would imagine she has not been working on it since. Or if she has been, she hasn't contacted me about it. Alright, let's see. Okay. Hey, Superbrain, how's it going? I see you in there. uh, Alright, so let's see. The stuff that she had been working on was how can we make a perfect... Nope. How can we make a magic square out of square numbers? And so the thought is that this has been long since, or this has been long since thought impossible. So her thought was, if we look at any one of these particular numbers where we have an intersection between a row and a column, and literally you could pick any row and any column. So if you want to target b squared or c squared or d squared or e squared or f squared, etc., you could do this by just picking the particular row and the particular column that match that thing. So the way she had done this was said that a squared. Let's not put that right there, shall we? Right, a squared plus b squared plus c squared is equal to a squared plus d squared plus g squared. Alright, she subtracted out all a squareds. Got rid of all that. And actually, moved c squared to the other side. And moved d squared to the other side. Okay, so this takes out a and c on the left and a and d on the right. And we're left with b squared minus d squared on the left. And g squared minus c squared on the right. Alright, so then the first step was to show that the cases that we have to deal with are going to collapse under squaring. So we're going to take g squared minus c squared mod 2 to the k. So when k equals 2 was actually the first one that she showed me how it all works, but we can get that in just a second here. So all right, so we take n mod 2 to the k being equivalent to 0, and we're going to find out that n is equal to some m times 2 to the k. So then, when we do n squared, we end up with an m squared times 2 to the 2k. And so this will be equivalent to 0 mod 2 to the k. So we can do some of these at least in general, and then we're going to need to actually break down. So if n mod 2 to the k is equivalent to 1, then n is going to be equal to m times 2 to the k plus 1. And so n squared is going to be equal to m squared times 2 to the 2k plus 2m times 2 to the k plus 1, which is going to be equivalent to 1 mod 2 to the k. If n mod 2 to the k is equivalent to 2, n is going to be equal to m times 2 to the k plus 2, and n squared is going to be equal to m squared times 2 to the 2k plus 4 m times 2 to the k plus 4. All right, and this is going to be equivalent to 4 mod 2 to the k. All right, so n squared in this case is going to be m squared 2 to the 2k plus 6m times 2 to the k plus 9, which is 9 mod 2 to the k. All right? All the 2 to the k's clean up in all these examples. All that's left over is the squared term at the end. And it's not really any secret here. These are going to become all perfect squares as we keep going down. All right. Then, at some point, this is actually going to start repeating itself due to the fact that eventually we're going to get a number which is going to be larger than the given 2 to the k, I think, right? Because, yeah, we're going to be squaring the number that we get over here for the modulus. And so when we square this number, it's going to have to be larger than 2 to the k due to the fact that, like, with, k being 3, we're going to get 8 here, but as soon as we get over the value of 3, then we're going to get 9. So that's that number, and any others will be larger. Then at this point, we start repeating values that we get over here. All right, so if we just extend this list as far as we want to go, then we're also going to notice that on the other end, n mod 2 to the k, if this is equivalent to -1, then we get our n equals m times 2 to the k plus, technically, right, this would be 2 to the k minus 1. Let me double check. Goodness. Good evening, everybody. I was not expecting potentially 5 or 10 people. I know it says 2, but I don't know. All right. So what we see here is that, right, when we have a mod value that gets us a -1, it's equivalent to saying, well, thank you for coming, Woodcraft. I will take any amount of lurk. So anyway, if you have a modulus that is equal to -1, then this is the same as having a value that is mod 2 to the k that is going to get you 2 to the k minus 1. So this is all going to end up being the same thing. So whether we have a modulus value of -1 or a modulus value of 2 to the k minus 1, it's going to be equivalent. So here we add 2 to the k minus 1 on the end, and this is going to be kind of our last, well, it will be. It'll be our last term before we go back to a modulus value of 0. So this is also equivalent to m plus 1 times 2 to the k minus 1. So if we want to find out, if we want to find out what n squared is, in this case, we're just going to, again, square what we just got there. So here this is going to be parentheses m plus 1 squared times 2 to the 2k minus 2 m plus 1 times 2 to the k plus 1. So again, here's the interesting thing, right? This is now going to be equivalent to 1 mod 2 to the k. So now we're starting to see these values come back again, and it's a little weird. It wasn't something that I was expecting, although I probably should have realized it. when I started doing this. Okay. So then we can also do n mod 2 to the k is equivalent to -2, which again, we can use n equals m times 2 to the k plus 2 to the k minus 2. So it's equivalent again to having a value which is 2 to the k minus 2. And you can argue about which one you want to do and which one is more appropriate or whatever you feel like. It doesn't matter. It's all cool. So here we still get m plus 1 again, in parentheses, multiplied by 2 to the k, and then minus 2 on the end. So then here, n squared, just the same as before, is going to now become m plus 1 squared times 2 to the 2k minus 2m plus 1 times 2 to the k. Nope, I'm sorry, that's wrong. Not minus 2. Oy. All right, minus 4. And plus 4 in the end, which again is equal to 4 mod 2 to the k. All right, so at this point, I'm looking at this, and I'm thinking that there's probably going to be a center of the list somewhere. So in theory, we're going to have n mod 2 to the k being equivalent to, and here we need like a middle of the list. So what's that going to build to on both sides? It should, in theory, be 2 to the k divided by 2. Or 2 to the k minus 1. Now check me on that, but I think that that should be the middle of, literal middle of the list. So we get a, right, our 2 to the k value would be technically the last one here, but that ends up being equivalent to 0, so. So anyway, I think that our modulus, middle of the modulus list should be 2 to the k minus 1. All right, so that means that n would be equal to m times 2 to the k plus 2 to the k minus 1. Okay, which at this point, I don't know. Can do a couple of things. So if we take out 2 to the k minus 1, so n equals m, nope, 2 to the k minus 1 multiplied by, we'd be left over with 2m plus 1, which is just going to be an odd integer. So unlike before, where we were left with all even integers, well, that's not really what we were going for anyway. We just said it was n integer, m plus 1, or m above, that we were multiplying by 2 to the k. So like we kind of need 2 to the k to be there. And if we try to take out 2 to the k, then we're going to be left with a plus 1/2. So like m plus a half. So then that is not an integer because m is an integer. So we got to leave it out and be separate. All right, let's just try doing n squared based on this. Let's see what we get. So this is going to be m squared times 2 to the 2k plus, here we're going to get twice that thing. Okay. All right, I think I'm okay now. So twice, this is going to be times m 2 to the k times 2 to the k minus 1. Plus 2 to the k minus 1. Okay, so this is going to be interesting here. Our 2 to the k, 2 to the 2k, and over here we have 2 to the, if we add these up, this is 2k minus 1 in our exponent, but then we've got this 2 here, which was created by the squaring. So now we do actually have 2 to the 2k, and this is m. Okay, so this is going to be m squared plus m parentheses. Yeah. Times 2 to the 2k. All right, plus this thing. Huh. All right, so plus the 2 to the k minus 1. That by itself is now going to be, right, equivalent to just 2 to the k minus 1 mod 2 to the k. Okay. So the center of our list is going to hit a max value at 1/2 the 1/2 this value. Right, whatever mod we're doing, the maximum value in the middle is going to be half that. I don't think it has to be maximum, actually, now that I'm looking at it. I mean, I guess it will be, because this stuff is going to wrap around depending on what 2 to the k is. Okay. So this is all fun. So we got a whole bunch of new ideas here that allow us to like collapse individual concepts via squaring, or collapse a bunch of the powers of 2 modulo arithmetic on powers of 2. Okay, so then this allows us to So group 2 here is all about taking g squared minus c squared and then taking some mod 2 to the k. Down to mod of modulus value of 2 to the k minus 1. So again, half of whatever we found. So either of these will exist. And require more testing. Or they don't exist. All right, so then last time I said here we were working with g squared minus c squared mod 2 to the k. Last time we said if g squared minus c squared mod 2 to the k were, again, let's just do k equals 2 for an example. G squared minus c squared mod 4 can either be equivalent to 0 or 1, and right, we can show, and in fact I showed last week, but we'll do it again, that these will collapse into either 0 or 1, and that's it. So due to the fact that they are squares, they can only be either 0 or 1. So let's just do that one more time, I guess. So if, let's see. Oh no, it was, we went. I'm fine. Okay, so we have the stuff up above. With mod 4, we've got either, again, here we've got a modulus value of 0 mod 4, 1 mod 4, 2 mod 4, or 3 mod 4 as our n values. Okay, so n mod 4 is going to be 0, so therefore n squared mod 0 is going to, or mod 4 is going to be 0. N mod 4 is 1, then n squared mod 4 is also 1. N mod 4 is 2. Then we end up with, again, a 4 at the last number, and that 4 ends up being, again, 4 mod 4 is 0. Nope. And n mod 4 is 3. Then n squared mod 4 is 9, which, you know, we get 9, and then mod 4 is going to be 1. So then we have a number of combinations that we can make with g squared and c squared. And as it turns out, right, g squared minus c squared mod 4, well, if they individually can only be 0 or 1 mod 4, then that limits our options here. If g is 0 mod 4 and c is 0 mod 4, then we can get 0. Or 1 and 1 mod 4, we'll get 0. If g is 1 and c is 0 mod 4, then we get 1. If g is 0 and c is 1, we get negative 1, which is the same as 3, which means that 2 is entirely off the menu. All right, so g squared minus c squared mod 4 can never be 2. All right, so then there was something else I did. All right. And I do mean I did, but yeah. And then I gotta check my student's notes because she had some other stuff. It wasn't quite as organized. Certainly not for my brain. But she also had a ton of notes on some other stuff. So right, so then we also had I was trying to write on paper. That wasn't going to happen. It's a stylus. All right, so at the same time, we also have b squared minus d squared mod 4, which again, going through the same process, if b and d are any one of these, again, 0, 1, 2, or 3 mod 4, then we're going to end up with the same results. So again, b squared minus d squared mod 4 can never be 2. All right, so then she had used a particular formulation and said that's a bad idea. All right, so she had used a particular formulation which said that g squared minus c squared was going to be equal to b squared minus d squared. B squared minus d squared is also the difference of squares, so b minus d, b plus d. Is equal to g squared minus c squared. And we should be able to divide one of these off. Now, specifically, she said in this case that b minus d is going to divide g squared minus c squared, and b plus d is going to divide g squared minus c squared. Right? Without loss of generality, it's all going to be the same thing. Alright, so this is when she started breaking down into cases, and it got really messy after this point, but it still worked out pretty well. So she said if we have g squared minus c squared mod 4 is equivalent to 0, then g squared mod 4 is going to be equal to c squared mod 4. Or, I guess, no, right, because, anyway, we already had the fact that up here, right, any n squared is either going to be 0 or 1 exclusively. So we can have any of these results here where your g mod 4 and c mod 4 are going to be 0, 1, 2, or 3. Could be any of them. But this is just going to say that, okay, these have to have the same modulus when you are squaring the individual terms. So then, if that's true, then either g mod 4 is equal to c mod 4, or g mod 4 is equal to c mod 4 plus 2. And again, by doing that, we could cycle that around and make it minus 2 as well. So, then this is where it gets fun, because I can only read about half of it. Okay. So this is where she then breaks down everything and decides we're also going to work in the mod 2 stuff at the same time. So is it odd or is it even? So anything that's even, as long as G and C are both even, then we're going to get something that is mod 4 equivalent to 0. And then we can't have anything that is of differing parity at this point, right? Because we were just saying what would happen if g squared minus c squared mod 4 is equivalent to 0. Okay, So that is also going to imply that okay, so that's going to imply that G and C have to have the same parity in this particular case. So that's not what I want. You know, n mod 2 have to be the same value. Okay, so then because of that, it's also going to have to be the case that B and D need to have the same parity as well. Again, either they're both even or they're both odd, I think. Let's make sure of that. So if G and C have the same parity, right, then we get an even number. So here we're going to have an even number, so they also have to have the same parity. Yep. Okay. Where do we go, huh? All right, so then the other option is that no, let's not do that. If g squared minus c squared mod 4 is 1, then g squared mod 4 equals, or is equivalent to 1, whereas c squared mod 4 is equivalent to 0. So g mod 4 would either have to have a value of 1 or 3, and c mod 4 would have to have a value of 0 or 2. So G and C have opposite parity. And therefore, B and D must be the same. All right, if g squared minus c squared mod 4, oops, forgot it in the last one, was equal to -1, or 3, whichever one we prefer here. Then, again, g squared mod 4 is going to be 0, sorry. And c squared mod 4 is going to have to be 1. So then g mod 4 is going to have to be either a 0 or 2. And c mod 4 will have to be our 1 and 3. So G and C are going to have opposite parity, so B and D are also going to have opposite parity. All right, so with that, I think it was at this point she bumped up to 8, but I'll have to check that again. Hey, Kiwi Gamer Romania, how's it going? You actually from New Zealand? I know you're in Romania. Or, I think. Yeah, New Zealand, Australia usually says oi in some capacity. I know a lot of British people do as well. So, I mean, stems from the same. Americans, not so much. Although I do, because I tend more British than a lot of my American compatriots. That's fair. Yeah. Yeah. I mean, since it was in your name, I figured either you were actually from there or just staying there. But either way, yep. That's fair. So tonight, anyway, we're working on this making a perfect square of, nope, sorry, magic square of squares problem that one of my students was working on back when I was her advisor for this. We met like 5 times, and then she just went off and tried to do something on her own, and then ended up on some completely different research project. No, so this is, like I said, this is just one of my old students' research projects that I never saw anything come of it. Um, yeah, so I also changed the background color. It's in the settings menu. You can, um, maybe not. Somewhere. I don't even remember where I did it. Yeah, there's a place in here somewhere which allowed me to change out the background color because it was just much nicer. Oh, okay. Eh, whatever. Yes, I've always used Microsoft Whiteboard, um, at least on this channel and my YouTube channel. So I have shrunk down my pen size a little bit. Um, although you've been here since that, but it's been it's been slightly annoying because I was using this one for a while, but like when I'm just trying to do something like this or like graph something, it was really distracting. Um, and other good news there. So other good news on that front, yeah, I have graph paper, so so I can actually use this, and like that was awesome. Um, do something like this and actually sort of see what I'm doing on a grid because this also has a miniature grid on it too. So I could really get in there if I felt like it. Oh, boo. All right, maybe that'll do it. There we go. So, I was looking at some stuff that my student was doing. Um, so going way back, she came up with or saw a problem which like Martin Gardner, who's really famous math puzzle kind of guy, was into, and it was trying to figure out the if you could make a perfect square. So that is, we start with um, 9 numbers in an arrangement like this with 3 columns, 3 rows, and all 3 of the rows, all 3 of the columns, and both diagonals are supposed to sum up to the same number all the way across. So the theory also for magic squares is that the numbers would be distinct from each other. So no repeats among any of them. That might be a bit of a challenge. So some people have argued that, well, maybe it doesn't have to be that way. Maybe we can have repeats. Um, Srinivasa Ramanujan, um, Indian mathematician from the early 1900s, came up with a formulation which helped him eliminate some of the possibilities of this and created a series of, I think, a system of equations basically to help him solve if this was possible. He didn't make much headway, but he also died super early. He was 38. I don't remember. It was way too early for him. Um, 1920 at the age of 33, 32. So way too early. Um, yeah. So he worked out a formulation where some of these things started eliminating, and so there's some interesting connections that are made. Yes, not Stone Age. No, he was in the he was born in 1887. So and died in 1907. Or wait, What did I just do? 1920. There we go. Wow. Yeah, he died in 1920, which again, far too early. Um, yeah, he had some really amazing talents, which unfortunately uh, were he did not get to share them with the rest of the world for very long. Um, he was a motorcycle repairman from India and like started teaching himself mathematics and tossed a few letters to some people in Cambridge and Oxford and said like, hey, I have some interesting ideas. And a lot of people laughed it off. They were just like, oh, pff, yeah, guy from India. There's no chance he's going to have anything interesting to say. And that was probably the biggest mistake that anyone could have ever have done. At some point, a guy named G.H. Hardy, who was another mathematician, decided, you know what? He has a couple of ideas that are really fascinating, and I've never seen them before. And most of the stuff is things that other people have done. But he was trying to like invent mathematics from the books he had available to him. And so he had these ideas in calculus and number theory and stuff like that that were completely novel, and then other ones that were like he knew he knew exactly what he was doing, but everybody else was thinking in terms of like modern notation, which Ramanujan did not know or have in some cases. So he like invented his own notation, and so everybody's like, I don't understand. And Hardy said, "There's something here." So he brought him to yeah, Trinity College in Cambridge, and um, like had him study up on like modern notation and all this stuff. But he had a big problem in that he, being a modern Hindu man, um, could not eat meat, and that was pretty much all that was here in England in the 1910s. Um, you know, every meal was like meat and potatoes. Yes, there are a few vegetables, but he was just like, okay, well, the vegetables are cooked in like beef broth, so I can't eat that. And so they did not know what to do with him. He ended up eating most of his meals just back in his room, making it himself. But at any rate, yeah, he he had very fascinating formulations, and he had some ideas about the magic square of squares, which some of which were able to pan out, and others he never got to finish it. So, and again, Martin Gardner looked at some of this, the mathematics puzzler, and I didn't wear the shirt today, but the yeah, Matt Parker from Stand Up Maths, who has been on Numberphile a bunch, uh, also did his own version where he did have like copied values in A and I and D and H and B and F. So they were like duplicate values along the diagonal or along some diagonal. And there's like argument, is that proper or anything like that? Well, it turned out that Matt Parker's doesn't actually add up to all the same number. All three rows, all three columns, and one of the diagonals, the main diagonal, add up to the same number. The off diagonal does not. It has since been termed the Parker square. If you haven't seen it, you should look up the video for Parker square on Numberphile because it's just funny. So, my student had done a bunch of stuff in Modulus 4, with Modulo 4, and said, okay, if we take g squared minus c squared, we're going to get these particular cases. So n mod 4 can be 0, 1, 2, or 3, depending on what number you have. And then if you square it, it turns out that you're only ever going to get 0 or 1 mod 4. That's it. So with it being only possibly 0 or 1, then you could work out like, okay, if g squared minus c squared mod 4 is 0, then it turns out that you have to have g and c being the same parity. So they have to have the same value mod 2. And then also, g squared minus c squared equals b squared minus d squared was an equation we pulled from the very beginning here. We said that all rows and all columns must be equal to each other, or must have the same sum. Sorry, must have the same sum. And they all have one term which is in common, whatever term that is. So for the top row and leftmost column, it's a squared. For, again, if we chose this row and the second column, it would be b squared, and third row, third column is going to be I squared, for example. So whatever rows you're picking, one of those terms will always subtract out from both sides, and it's gone. Then you can subtract one of the terms from either side, or, well, subtract terms from both sides and cross them over. And so we end up with b squared minus d squared is equal to g squared minus c squared. So then we want to look at what happens when we do g squared minus c squared mod 2 to the k. So some power of 2. Well, at the bottom here, we said if we get g squared minus c squared mod 4, so k equals 2, for example, equal to 0, then we end up with g squared mod 4. It has to be the same as c squared mod 4, and so therefore either they have exactly the same modulo value mod 4, or they're off by 2, and then when you square it, they both drop to the same number. They both become 0, or potentially both become 1. So it tells us that g and c must have the same parity, and therefore b and d must also have the same parity. And then if you get either 1 or negative 1 as your mod 4 value, then it turns out that they must all have the opposite parity as each other. So g and c must be opposite, and b and d must be opposite. Hopefully that makes sense. Ooh. Yeah. And one of the other things that's really super important is understanding the diversity of knowledge we have in the world. Because, again, like we saw with Ramanujan, if you take for granted the idea, which is false, by the way, that people from certain places have no inherent, like, knowledge value for any particular subject. Okay, it's wrong. It's very wrong, and demonstrably wrong. Again, Ramanujan was the example that proves this point. This guy taught himself mathematics, and not to mention, less than a couple hundred, or less, well, I don't know, whatever. A few hundred years earlier, India had been the center of mathematics in the entire world. Like, the reason that Islamic mathematics existed was because of Indian mathematics. And it's just, yeah, it doesn't work like that. There is absolutely no, difference between any particular group of people. It's, even if there is some slight variation, it's going to be slight. And the nurture factor, right? What you choose to do with your life and what has been chosen for you by your culture far overrides any sort of perceived difference in any other factor. Well, yes. People who discriminate are causing the problems, yes. Yeah, and if only people would figure this out faster, we could start getting all sorts of people from all sorts of backgrounds and understand. And it's only harming everybody. Well, I mean, I prefer keeping my brain intact. Oh, you mean I I get what you're saying now. Yeah. Yeah, if people actually used half their brain, it would be nice. Um, sorry. No, that was a good idiom. Good job. Um, like I would argue that this is, wasting brain power on that sort of, nationalism, culturalism, whatever, is just ruining our possible advances and the kind of gains that our entire society could make. Yeah, usually said right before they get taken down a couple of pegs. So I just had a thought here too. I don't think it's gonna I don't think it's gonna pan out at all. But the other thing would be that we could take this group here, and now we have like this triangle that's going with all three of these groups. So I don't know if this would help at all, like adding a third one in to make like a triangle here. Yeah, there is no greatest. There is only Zool. There is only like what is your society doing for everybody? What is it doing for humanity? And I mean, like 20 years ago, even less than 20 years ago, at my college, we were pulling people in from um, we had so many people coming to our school from India and China because they wanted to go to the University of New Hampshire. And I mean, being somebody who went to the University of New Hampshire, I had no idea why. It's like, what? Here? Really? Um, but like we had so many people from these other countries. It was so great to like finally get to talk to them and mix our cultural knowledge and be like, oh, what did you guys learn growing up? Oh, what did you learn growing up? And talking math with each other. It was just great. I loved it. I wish I could remember half of the actual conversations that went on, but like I said, it's been almost 20 years. That's the other thing now is that both China and India are doing great advances, and a lot of these students went back home and are now making some sort of awesome contribution to their society back home, and now they're going to be, um, you know, they're going to have centers of education which are going to be sought out by Americans in, I'm going to predict like less than 50 years. Yeah. If only they could actually like be around and work with smart women, they would realize that yeah, there's no you're wrong. There's no greater group of people. You just got to think. All right, so if we went this other way, so for the top two, that's going to get b squared plus c squared is equal to c squared plus e squared plus f, no, g squared. So those are going to eliminate, and then we get b squared minus, it's going to be minus a squared. B squared minus g squared equals e squared minus a squared. Right, like it doesn't particularly matter what order we put these in. We could swap e to this side and do the exact same stuff. So it doesn't particularly matter. But then at the same time, we have ADG in the column. C squared plus E squared plus G squared. All right, G squareds are out. And then we get move the first one that's remaining. I don't know. Again, it doesn't particularly matter how you do it, but we subtract out the g's, a squared minus e squared, or a squared minus c squared equal to, here would be d. We could switch to a squared instead. That's not what I wanted. All right, and this one could be e squared. That's what I meant. You know, the worst part is that it's not just like religious extremists. You've got people like you've got people like Richard Dawkins and people like that who have been, misogynistic all along, and maybe they kept it under wraps, but I think he in particular got old and cranky and decided to throw that out there. And like, there have been a lot of scientists where, and this is true in old days as well as some of the newer ones. There have been so many scientists where it's been like, oh well, I used to respect you before that opinion came out. Well, it's not only that, but yeah, pretty much. It's some sort of, oftentimes it can be power play. So, I mean, guys like that are abusive and will go to any length, which does also include like, getting some other family who is on their side to then like forcibly marry their daughter for political gain or power gain or all sorts of, it's just, it's not cool. Anyway, um, okay. I'm not sure if there's any other connection I can make here other than like the same ones I had down below. So, like each of these things on either side has to have either the same parity or the opposite parity, depending on the uh, modulo value mod 4. And let's see. Hmm. Okay, if I added these equations together, I think I just end up back with the other ones that I started with. So, yeah, probably. Minus c squared, b squared minus d squared, yeah. So, I end up back with these same equations anyway. No. Okay. Grab the wrong thing. Yeah. I mean, studying physics at the very least will start getting you a sense of like how this stuff can be applied and how to formulate a mathematical problem from a physical one. So being able to understand, the complicated stuff that's behind all of this, what are all the forces, how do they play with each other, that sort of stuff. Um, yeah, then you get a teaching job. So theoretical mathematicians are not necessarily unaware, right? The one guy that I was talking about there, the one guy I was talking about who wanted his work to be completely divorced from reality, uh, you know, that was an interesting scenario. Um, yes, please do not become a teacher if you don't want to be there. Yeah, high school teachers are not well, or basically any teacher K through 12, public school is not very well paid here at all. Um, there are certain districts which do a decent job at keeping their pay, somewhat manageable. But a lot of places it's just ridiculous. I know for a fact that like had I been in the corporate job that I had also applied for at the same time, I would be probably making close to twice what I am now. But I don't know how miserable I would be. Yeah. Yeah. So one of the things that I did was, I had married somebody who who did have a good well-paying job, while I was earning basically half of what I am now, uh, as a substitute teacher and also at that insurance agency that I was talking about before, doing what a bunch of people with bachelor's degrees were doing, and most of them have bachelor's degrees in completely irrelevant areas compared to what we were doing. So it was just like, oh, I had a degree in English or general studies or whatever else, and it, a few people in business, they were looking to do their own businesses at some point. Um, but yeah, like I was probably the only person who had been in math. One of my friends was in computer science, and he wanted to get a job in IT. So he had to go through this temp job that I was also in order to get to IT in the same building. Um, I don't know if he actually ever did make it in there, or if he's just been kind of doing something similar. Uh, haven't haven't talked to him in a couple of years. Maybe it's about time to see what he's up to. But yeah, the other thing about like mathematics in particular is as long as you know how it all works, you can find the mathematics in your job wherever you are, and kind of start hammering away at it. I mean, uh-oh, if we think about it, I typically tend to agree with that. Um, when I had initially joined college, my no, I mean that's field of study. Yeah, but generally field of study. That's fine. It's you could use that either. Um, when I had joined the physics department, the physics teacher had said this is the most applicable major because you're looking at all of the physical situations, and basically you can inform the engineers, the mathematicians, and you can inform like everybody about what kind of stuff is going on, and it's the most applicable potentially, but maybe. I mean, it depends, right? Because like I only studied up through linear algebra, which um, what were the other senior level classes I did? I don't even remember. Um, also potentially true. So I do whenever I do programming, I tend to use a lot of algebra and algorithmic thinking, and so it's just a matter of like what can I, what do I need to repeat? Like what things do I need to plug in here and create for loop? Well, not for loops anymore, I guess, but what while loops do I need to create? What kinds of things can I automatically iterate? And then once we get into that, then like all of my algebra kind of feeds into it. I mean, that's kind of what I did at that job. I was I was just bored. So I was like, you know what? I'm just gonna program myself out of a job. That's fine. I'm cool with that. Because I didn't want to type for 2 hours to do one file. I was just like, no, this is not how this works. So I was like, I can just automate this. So I read all of the information, I put it to an array somewhere, and then started reading the array one element at a time, cross-referencing it with another array, putting all the information in array number three, copy pasting that into the provider's file, and then iterating to the next one. It was great. My boss just about, yeah, uh, my boss just about like Uh, she was about to kill me because she didn't understand what I was doing. She thought I was just manipulating the system and like giving myself credit for doing something that I didn't actually do. And I was like, no, 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 no. If there's one thing that I am, it is honest, and I will show you exactly how it works. So I showed her exactly how it works. And then they ended up giving me a $750 bonus. It wasn't nearly as much money as like the amount of work I did technically, but whatever, it was fine. It basically doubled my paycheck for, a week or whatever it was. God, how much was I earning? That was an awful that was an awful paycheck, but so it was kind of interesting. It was like, you get 32,000 or something like that, and I was prorated because I was only working 30 hours instead of 40. So, hooray. But then I was also doing my master's, and I was also um, doing adjunct faculty position at this same college. So I was at least, I was basically getting paid an extra $3,000 every semester to teach math, which I wanted to do anyway. So, okay, teach one class every semester. All right. Let's just check something here anyway. So we also work with g squared minus c squared mod 8. So then we have to do this whole, well, actually we have it in general up here. So we can get 0 through 7 as our possible moduli. And mod 8, 0, 1, 2, 3, 4, 5, 6, or 7. And what is n squared mod 8? So these are going to be just the square numbers of whatever the end is here. So this is going to be 0, which is just 0 mod 8, 1, 4, and then here 3 is going to become 1. 4 is going to become 16. 16 mod 8 is 0. Right, and that's the halfway mark through the list. So this, yeah, okay. And then we got 141 again, right? Should be 141. So let's check. 5 squared is 25 is 1 mod 8, or 25. 25 mod 8 is 1. 36 mod 8 is 4, and 49 mod 8 is 1. Cool. And then obviously 8 is 0 again. So we have this nice pattern that repeats itself over and over again. So we get 0, 1, or 4 as our possible n squared mod 8. So g squared mod 8 okay, is there a pattern here? It's every other if odd, and then here if it's 1 and 4 or 2 and 6, those are going to be equal. either they're equal or g squared mod 8 is going to be equal to um, 2m plus c squared mod 8 if odd. So our class, discrete structures, is basically math proof. There's some other bits to it, but it's essentially a math proof class. I think the discrete math that I usually see is like college prep high school classes, or maybe so it's looking specifically at like doing series and sequences. It's looking at doing combinatorics, stuff that involves um, discrete individual values for mhm. Yeah. So basic proof techniques are, I mean, in order to prove relationships, right, then you're going to be looking at trying to do these um, proof techniques. So you can, again, do a direct proof by contradiction, so show that something is obviously wrong and therefore it must be the other way. um, Goodness. All right. Any integer greater than or equal to 8 can be written in the form 3x plus 5y. Do x and y need to be integers themselves? Yeah, yeah, that's fair. I think you could also come up with an interesting proof with using modular arithmetic. Maybe. Because I think you can fill in every blank by using that particular setup. And all numbers can be written as either 0, 1, or 2 mod 3. Adding 1, 5 allows you to be on allows you to get to 2 on mod 3. Because 5 itself has a remainder of 1, or sorry, remainder of 2 when you divide by 3. And then, right, twice 5 is going to be a remainder 1 mod 3. So any number of 3's is going to allow you to get to, again, 1. Yeah, that's what it is. It's if you have 1, 5, then any number of 3's after that is always going to get you to all of the remainder 2's. And then if you have 2 5's, any number of 3's will get you to all of the remainder 1's. And then any number of 3's will get you to the remainder 0's. So just doing that is, yeah. Yeah. K plus 1 is 11, then by induction hypothesis, is this integers such that k plus 1 minus 3 equals 3a plus 5b implies that k plus 1 is equal to 3 times a plus 1 plus 5b. Yeah. Yeah. I mean, it looks reasonable. All right. Anybody else out there in math land want to offer any suggestions? Have any questions? Alright, so let's see, what else could we get? G squared minus C squared mod 8 could be equivalent to... Alright, give me 1 second. Righto. So let's see, options. So g squared minus c squared mod 8. You could have 0 for g squared, which would then allow this to be -1 or -4. -4 is going to be equivalent to +4. Zero. All right, if g is 0, then c could also be 1. -1. Right. Can't get +4 for this one. At least not the way that I'm thinking of it right now. If g squared is 1, then we could have -1, which is 0, -0, which is 1, or -4, which is going to get -3. If g squared is 4, then we can have +4. We could have 4 minus 1 is 3. 4 minus 0, 4 minus 1, and 4 minus 4 is 0 again. 4, 5, 6, 7. All right, so 7 different cases. But again, 4 and -4 are the same. So if we write the distinct values of n squared mod 8, this is going to be 0, 1, 3, 4, -3 is 5, 7. So there's 6 possibilities here. Cool. Okay, so if g squared minus c squared mod 8 is 1, then that means that we must have had a 1 and a 0. So g squared is 1. It pretty much just, it forces it. Right, that's the only possibility. So g squared is one of our 1s here, and c squared is our 0. Because any other combination, you're not getting a difference of 1 in their moduli. So therefore, g squared is odd. And c squared is even. No, not even. It has to be 0. So c squared is c squared mod 8 is either going to be 0 or 4. No, that's not what I wanted. Sorry, c mod 8. G is odd. There we go. So G is odd. C mod 8 is 0 or 4. Right, those are the only possibilities. Alright, then we've got 3, which is again G squared minus C squared mod 8 is equivalent to 3. Then G squared mod 8 must have been 4. And C squared mod 8 must be 1. Again, no other possibilities to get 3. If G squared mod C squared mod 8 is 4, then we must have had a 4 and a 0. Oh, or it could be the other way. Right, because I incorporated negative 4 as well. G squared mod 8 is going to be 0 or 4 in that order, whereas C squared mod 8 must be 4 or 0 in that order. So they must correspond exactly. 0 to 4 or 4 to 0. If G squared minus C squared mod 8 is 5, then this is negative 3. So G squared mod 8 would have to be 1. And C squared mod 8 would have to be 4. So 1 minus 4 mod 8 is going to be negative 3 mod 8, which is positive 5. G squared minus C squared mod 8 is 7. And G squared mod 8 would have to be 1. And C squared mod 8 is going to need to be 4. To get us a... Nope, sorry, wait. Man, I just did that. Wow. Alright, 0. G squared has to be 0. C squared has to be 1. Okay. Alright. So then, this says we've got G squared mod 8 is 4. That means that it must be either, what is that, 2 or 6. So G mod 8 must be 2 or 6. And C mod 8 must be, oh, well. C is just odd. Right, any odd value. G squared mod 8 is either 0 or 4, so it's even. G is even. And C squared mod 8 is also even. But the opposite kind of even number. Is it divisible by 4? Right? Either it's 0 or 4, or it's 2 and 6. Aha. So it definitely has to be even regardless, but G mod 4 equals 0 and C mod 4 equals, is equivalent to 2 or other way around. G mod 4 is 2 and C mod 4 is 0. Okay. G squared mod 8 is 1, so G is odd. And C squared mod 8 is 4. So it's only 4 when it's not divisible. So mod C mod 4 is 2. G squared minus C squared mod 8 is 7. Means that G squared mod 8 is 0. So G squared mod 8 is 0. So it's divisible by 4, or G mod 4 is equivalent to 0. And other side, C squared mod 8 is 1, means that C is odd. All right, so we may have eliminated some possible cases here, potentially. All right. Anyway, we're running up against end of time here, so let's see who else is on today. Alright, as always, Jason is on. Oh, interesting. We don't have... Have I not followed? Alright, Commander Tolian, thank you for sending in the follow. That was before stream, but still, you know, it counts. Oh, okay. Megalomorph is on, so I think we're going to send people over his way. Megalomorph is another mathematics type streamer. His stuff is usually a little bit higher level, so I try to tend to keep my topics kind of in like number theory and like stuff you'll run into in first 2 years of math at either a university or a 2-year college, naturally. Or do some interesting research that's like just around that level. Megalomorph, I believe, is a grad student or lecturer. I don't remember exactly. In and around that area, so he does more like grad student type stuff. So we're gonna send us over that way. All right. So thank you everybody for coming. We're going to raid over to Megalomorph, and I hope to see you either on Friday for maybe. He makes me confused too, but he's good at explaining stuff. Yeah, you too, Kiwi Gamer. Thank you for coming. um, so whatever I was gonna say. Yeah, I'll probably see you on Friday for we're gonna try to finish up Outer Wilds DLC because man, I'm like so close to it. Um, and we'll be back next Wednesday for another math stream. So, have a good night, everybody. This is Obi-Wan Pez for N Simplex Pachinko. We're going to head on over to Megalomorph's channel in just a few seconds here. So, thanks everybody for coming yet again. I know I say it all the time, but still. Good night.